Welcome to today's video, 5 top tips on Born Haber cycles. Hello everybody, for today's 5 top tips on Born Haber cycles video, I'm going to be using this past exam question, which is an AQA past paper question, but the format of the OCRA past paper questions on Born Haber cycles are much the same. Now, the reason I've chosen this particular question is because this layout for a Born Haber cycle question is extremely common, and it showcases what you are expected to do with the Born Haber cycle, i.e. filling in the missing species on these lines. It then gives you a table of data so you can see how that information may be presented, and then it's asking us to do a Hess's law calculation to work out one of these processes. So my 5 top tips are all based on how we go about labelling up the Born Haber cycle, how we then put this data onto here, and then how we go about doing the Hess's law aspect of the calculation and what I would choose to lay out in my working. So I'm going to utilise this question today to showcase my 5 top tips on Born Haber cycles. So let's get going. Okay, so the first part of this question was asking us to complete the Born Haber cycle by writing the appropriate chemical formulae with state symbols onto the dotted lines. Now, in this particular type of question, they will usually have already written on some of the chemical formula for some of the different stages, and in my experience, they tend to always go for these 3 being filled in, and you will be asked to fill in these ones here. So we always start with the ionic compound in its solid form at the bottom, and what we're saying essentially is there are 2 ways we can make this. 1 from the elements in their standard states, 2 from the ions in the gas phase. Now, Hess's law said that it doesn't matter whether we can't find out the value of a process directly, we can start and finish at the same place and work our way around the cycle in a different route and still end up with the same answer. So what we need to be able to do on a Born Haber cycle is figure out how we can go from magnesium in its solid form, in its standard state, to magnesium ions in the gas phase, and how we can go from chlorine as a diatomic gas in its standard state to 2 moles of chloride ions in the gas phase. And that's what these steps here are going to enable us to do. So my first top tip is always do these steps in the same order. Now, there are some steps that are non-negotiable and you can't do in a different order, but since I learned how to do this during my own A-level, have always done these steps in the same order because it's routine, it's structure, it just makes life a whole lot easier in my opinion. So the first thing that I would always focus on is the metal. So the first thing I'm going to do is work out how I can turn my magnesium solid into Mg2 plus gaseous ions. So the first thing I'm going to need to do is turn it into a gas, and that's because in order to do first and second ionization energies, I need my magnesium atoms in the gas phase. So that's enthalpy of atomization of magnesium. Then we've got the first ionization of magnesium. Then we've got the second ionization energy of magnesium. And then the magnesium is ready. Now I'm going to focus on my non-metal, so my Cl2 gaseous molecules. I need to first of all turn those into atoms, and then once those are atoms, I can then turn those into ions via electron affinity. So for these 4 processes here, I would always have my metal turned into a gas first, then all the relevant ionization energies that you need. Then, and only then, would I start to work on my non-metal, if we've got molecules, turning them into atoms, and then from atoms, turning those into ions. So keeping those in the same order all the time is top tip number 1. For top tip number 2, I'm focusing on taking the values from the table for the different processes and adding them onto the Born Haber cycle. Now, this isn't essential, but as somebody who's a very visual learner and likes to see everything laid out, I think this is a particularly helpful thing to do. Otherwise, you're going to be trying to do far too many steps down at the bottom here. But in order for us to add these numbers onto the Born Haber cycle, we need to know what all of these different processes are called, because they have listed them not in order, as in not kind of each process in turn. They've put them in a completely random order, so you need to know where the enthalpy of atomization of chlorine is on our Born Haber cycle, which is up here. What we would then be able to do is work out which piece of information we are missing. Now, lots of Born Haber cycle questions will ask you to calculate this value here, which is the lattice enthalpy of formation. However, we have been given this in the table. So when I've put all my values on, I can see that it is this process that is missing, which is the second ionization energy of magnesium. So I've put a little X there to show that that's what I'm trying to work out. Some of these values you may see I've had to multiply by 2. So in and amongst this tip, there's kind of like a second tip, tip 2 part 2 if you will. All of these values are kilojoules per mole. And if we were to look at the definition of all of these processes, it's always 1 mole of gaseous chlorine atoms being formed, 1 mole of gaseous magnesium atoms being formed, 1 mole of a compound being formed from its elements in their standard states. So the per mole bit is really important, because what we can see up here, when we do the enthalpy of atomization of chlorine, we actually make 2 moles of chlorine atoms. So I have to multiply that value by 2, because the plus 121 kilojoules per mole is for 1 mole, and I'm forming 2. Likewise, for the electron affinity, I'm taking 2 moles of gaseous atoms and I'm forming 2 moles of gaseous chloride ions. Because the electron affinity value is per mole of these that are made, and I'm making 2 moles of Cl- ions, again I have to multiply that number by 2. They're the only places on this particular Born Haber cycle that happens, but it will differ for different ionic compounds. So just always go back to thinking about the definition and the fact that these values are per mole. So anytime you are forming 2 or 3 or 4 or any different number of moles of something in a particular step, remember to multiply that number by 2, 3, 4, 5, whatever you need to. Okay, so that's tip 2. So top tip number 3 is adding your Hess's law arrows to enable us to calculate a value for the unknown process. In this case, the second ionization energy of magnesium is what I want to know. Now I've written a little S for start and E for end. So Hess said that we have to start and end in the same place, but we can work our way around the cycle the opposite way. So we can't go directly from the start to the end, and that is the start because that's where the arrow starts, and that's the end because that's where the arrowhead ends. But we can work our way the other way around the cycle. So I've then added from the start point arrows that take me the other way around my cycle to the same end point. And I again would always visually add these arrows on, because especially when you're learning, even if you weren't to do it in the exam, because it's going to help you with tip 4, which is thinking about what we're going to need to do with some of these numbers. Okay, so top tip number 4 is changing any of the values where the Hess's law arrow that we've added goes in the opposite direction to the arrow on our Born Haber cycle. So if we're starting at S and working our way around the cycle this way towards the end point, the Hess's law arrow for the first ionization energy of magnesium is going the other way. So it'll now be minus 736. The arrow for the enthalpy of atomization, we've gone against that as well. So I've made that minus 150 there. This process here, which is the enthalpy of formation, the Hess's law arrow goes in the same direction. So that number stays the same. Haven't rewritten it in the turquoise pen, I've left it as it is. Both of the Hess's law arrows on the right hand side go in the opposite direction to the original. So again, I've changed the sign there to plus 2493, and I've changed the sign here to plus 364 times 2. And then the final arrow up here is coming down for the Hess's law arrow when originally it was going up. So again, I've changed the sign there. Again, I know this feels like quite a lot of steps, but the students who try and do all of this in their head in one go are far more likely, in my experience, to make mistakes than those people who write out the values as they are and then the corrected values for the Hess's law cycle. Now I've done that, I can get my final answer and I can give you top tip number 5. So tip 5, to finish off, is once you've calculated your value, and I got an answer of 1,451 kilojoules per mole here for the value for X, which is the value for the second ionisation energy of magnesium, I would always just be checking on my Born Haber cycle, the arrow for the second ionisation enthalpy of magnesium is pointing upwards. And on a Born Haber cycle, all of the arrows that point upwards represent endothermic processes, and all of the arrows that point down represent exothermic processes. So I would be expecting to get a value for X which is positive, which I did, which is a nice little check just to make sure that you are potentially correct. Another thing we might want to check for ionisation energy is what was the value for the first ionisation energy, 736. The second ionisation energy should always be higher than the first, which it is, which is another good little check. And what you might can see here is I've written out all my working out here, which I will always recommend. And if you've watched my videos before, or I've taught or tutored you before, you will know that I am always banging on about showing all of your working out. But you might also notice what I've done here is for each of the values, I've always put the positive add sign in between, because what Hess said is we can go around the cycle the other way, but we have to add all of those different stages together. So even though I've written that we're going to add a negative number, and I know that that means we're going to take that number away, I'm quite picky and I like to write it as plus minus 150, plus minus 642, because again, if I'm trying to do too many steps in one go, I'm likely to make a mistake. Now I put all of that on my calculator and I get the right answer. If you want to just write that as minus 736 minus 150, you can do. But if you are worried about getting the signs the wrong way round or getting muddled up, I'd recommend putting your plus signs in, because Hess did say we have to add all those various steps together. That will be our final answer. Always check whether it's positive or negative and whether it should be positive or negative. And there you have it. 5 top tips on Born Haber cycles. Thank you so much for watching. I hope you found it helpful.